Hello, welcome to the final video in this first AP online maths lesson. So this one is the one I promised in the previous video, which are past paper examples based on ln of x and e to the power of x. So we're just going to do a selection of problems. Obviously, if you go onto the St. Maths website, you have access to all the past AP Maths papers. So you can go and you can look at more complicated, well, not really that there is much more complicated examples than the ones I'm doing with you guys now, but you can definitely go and you can look at some other examples. So first example we're going to do over here, and you'll see, I'm just going to zoom in a little bit so you guys can hopefully see this a bit better. There we go. Technical issues solved, hopefully. Now, this one specifically is from the AP Maths paper 1, and it's from the 2019 paper. So this is last year's AP Maths paper. And I want to focus on question 1.1b. And it says, e to the power of x plus 12e to the power of minus x is equal to 8. So let's copy that down. So we've got e to the power of x plus 12e to the power of minus x is equal to 8. Now this is very similar to the example that we did from the textbook. The only difference we have here is we've got that e to the power of minus x, which if you recall is going to become e to the power of x plus 12 over e to the power of x. And then that again means we've got an equation with a fraction. So we need to multiply by that LCM of the denominator. So I'm going to multiply by e to the power of x. And then, careful, e to the power of x times e to the power of x is e to the power of 2x. Because when I multiply these two and the bases are the same, I add the exponents, saying it's x plus x, which is 2x. Now, I'm going to rearrange it as well, because you should notice that I'm going to multiply that 8 by e to the power of x, which then means this is going to be minus 8 e to the power of x. And I'm going to multiply the fraction by e to the power of x, which means e to the power of x divides into e to the power of x, so I have 12 over here. And that is exactly like the one in the previous video, which just involves factorizing because it's a quadratic trinomial, exponential, but it's effectively a quadratic trinomial. So we factorize, and we say it's e to the power of x times e to the power of x, and then that 12 is going to be 6 times 2. And it's got to be minus 6, and it's got to be minus 2. So I've got the minus 6 e to the power of x minus 2 e to the power of x is minus 8 e to the power of x. That then gives me e to the power of x, which is equal to 6, or e to the power of x, which is equal to 2. And then finally, I can then go and say I need x to be the subject or the output. Currently it's the input, but the only way I can change it from that position to this position is to then go and use the inverse function, which we now know is ln or log. So it's log base e, which is ln of 6 in this case. Or in this one, x is going to be equal to log base e, which is ln of that number 2. And again, depending on the question, in this particular question, they said, solve for x, an element of the real numbers, without using a calculator showing all your working. So if you look here, it says there, without using a calculator showing all your working. So because of that, you can't use the calculator to now go and simplify this correct to 2 decimal places. Nope, you're going to have to stick with this version of the answer. So that's the first past paper example. Let's look at the next one. The next past paper example, there we go, comes specifically from, down here at the bottom, you'll always see the date, the 2018 AP Maths exam. Okay. Now, the first one is also, again, a lot like the example we had in the textbook. Slightly trickier, but actually very simple in the end. You'll see just now what I mean with the slightly trickier, because you haven't seen one like this. But eventually, this does get solved very easily, even in spite of the fact that it counts 6 marks. So, when you look at this one, the first thing that you need to notice is you need to notice that the bases are the same. Well, how do I know the bases are the same? Because I've got ln there and I've got ln there, which means it's log base e there and it's log base e there. So let's copy this down. Right, so there is my problem. Now, currently with that 2 in front, that's a little bit of a problem. I can't use law 1, which means if I add two logarithms and the bases are the same, I multiply these numbers. I can't currently do that because of this 2. But luckily, I've got law 3, which means I can move the 2 up. So I'm going to show you what happens here with all the steps. It's the ln of x to the power of 3 plus the ln of x squared, but that 2 is now going to move over there. So please be careful, the 2 doesn't move over the entire function, it only goes to the number there, and that's going to be equal to 7. So I've got the ln of x to the power of 3 plus the ln of x to the power of 4 is equal to 7. Now I've solved my problem, because now I've got two logarithms that are being added together, and specifically because the bases are the same, meaning that both of them has that base of e, I can now go and I can say, make that one ln or log, where it goes x to the power of 3 times x to the power of 4, and that is going to be equal to 7. So that then gives me ln of x to the power of 7 is equal to 7, and then I can go and I can say quite easily, now I've got that base e over here, because remember it's log base e, x to the power of 7 is equal to 7. So the last little step over here is then again to say, I now need to go and rearrange this, going from log form into exponential form. So again, please remember there's a little base e over there, so it's e to the power of 7 is equal to x to the power of 7. So let's write that down, e to the power of 7 is equal to x to the power of 7. And hopefully you can spot the equivalence over here. The equivalence meaning if the left-hand side has got to be equal to the right-hand side and the exponents are the same, then logically speaking, my basis must be the same. So therefore, I can end off saying x is equal to e. So it actually ended up being a very, very simple equation. It did have a little bit of tricks because it's strange, and I mean, I don't think there's another example quite like this in the textbook, but once you follow through and you just keep on going, you realize this was actually pretty easy and straightforward, and it gives you a nice simple answer. Right, now the next one is in that same paper, the 2018 paper. And this one, number 1.2, is something that's actually quite common. If you start going through past papers, you'll see they love putting these little word sums into your exponential and ln. So this one states, the equation for radioactive decay of a radioactive element is given by this. Y is equal to y0, e to the power of minus kt, and they give you the fact that k is greater than 0. So please note, there's a restriction, k has got to be equal to 0. And then they tell you a little bit of information about this. They say y0 is the initial amount. In other words, if you're talking about radioactive decay, then you would have to have an initial amount of radioactive material that is going to decay over time. So depending on what that initial amount of radioactive material is, obviously it's going to change what happens with the decay of the radioactive material. Y is the amount of time, t in years, and k is a constant. So very important, this part, please people, I'm going to highlight this because we're going to get back to this. K is a constant. So k is not a variable, k is a constant. The half-life of an element is the time taken for half of the quantity to decay. So when they talk about radioactive material, they talk about half-life in the sense of how long will this take to only now have half of the quantity that you originally started with. Now the first question, they say, make k the subject of the formula. Now this is a literal equation, and a literal equation pretty much means solve for k. So you want to go back to this equation and you want to solve for k. You want to make k the subject of the formula. So let's copy that down. Okay, here's a piece of paper, and we'll say the a part of this sum, we start with the original equation y is equal to y0, e to the power of minus kt. Now please remember, this is not the same thing. y0 is the initial amount and y is whatever is left after a certain period of time. So please do not get confused and think this is the same thing. They are not like terms, they are very much two different things. So y and y0, you can't add them or divide by them, they're two different things. It's almost like saying this is A and this is B, not the same thing. Okay, right, so now I want to go and I want to make k the subject of the formula. So the first thing I need to realize is I'm going to have to divide both sides by y to the power of 0. So I've got y divided by y to the power of 0 is then equal to e to the power of minus kt. Now, this then is an exponential equation. So I've got the base to the power of minus kt is then equal to that y over y0. And I'm now again going to have to go, and if I want to solve an exponential equation, realize I need to use a logarithm. But because of the base e, my logarithm is going to be ln. So I start off by saying here, this is currently my input. I want to make my input my output, so I want to go and say it's minus kt. In order to make my input my output, I need to use the inverse function, which is log, or in this case ln, because the base is e. So it's log base e, which is ln. And then this, the number, goes over here, y over y0. There we go. And then we're almost done, because like I said, we're trying to solve for k. So if I try and solve for k, I'm going to divide both sides, careful, by negative t. So I get k on its own. So k is then going to be equal to the ln of y over y0 divided by negative t. And I've answered the question, which is make k the subject of the formula. So that's the first part of this question. The next part of the question then says, determine the value of k for carbon-14 if the half-life of carbon-14 is 5,700 years. Give the answer correct to 6 decimal places. Now the reason this only counts 2 marks is because it's a follow-up question from the previous one. You've now made k the subject of the formula, and now they ask you to determine the value of k. So please do not go and do everything again. Use the formula you've determined. So using that formula, the first thing we have to do is we have to realize they said determine the value of k if the half-life of carbon-14 is 5,700 years. So we are saying that k is equal to ln, and now the half-life says that this from the original, if I look up here, from the original initial amount, it is now halved. So that means if I go and I set y0 equal to 1, then this is going to be half of the original amount, which is a half. Or if I say y0 is equal to 4, then this would be half of the original amount, which would be 2. But whichever way you go, you should recognize that if I divide what it now is by the original, it's a half, because it's the half-life. Okay. Then they also give me the information, and they say the half-life of this carbon element is 5,700 years. Here it is. So that information, the half-life is 5,700 years. And that, logically speaking, is t, because they told me time in years. So t is 5,700 years. So I'm going to substitute that t with 5,700. There you go. Great. So now all I need is I need a calculator to work out the value of k. And I start by saying it's ln. So obviously your ln button is over there. You could use log base e, but I mean ln is already log base e. So it's the ln of a half over minus 5,700. And that gives me a k value of 1,22 times 10 to the power of negative 4. So you can keep it like that in your your scientific notation. So you can keep that in your scientific notation. They're perfectly happy with that. And we're going to round it off to 2 decimal places, because in AP Mathematics, they always ask for 2 decimal places. Just realized something. Read the instructions. Give the answer correct to 6 decimal places. Read the instructions. That was almost a big mistake on my part. So we're not going to do that. We're going to say it's equal to 1,21604. So that's 1, 2, 3, 4, 5, and then 8. That'll be my 6 decimal places times 10 to the power of negative 4. So there we go. That is the answer they were wanting. Okay, now the last little question over here. C says, how old is a sample in which 10% of the carbon-14 nuclei originally present have decayed? In other words, 90% of the original quantity remains. So they tried to make it very, very clear. They said to you that 10% has now decayed, which means there's still 90% left. And they're asking how old it is. So I'm going to go back to this version of the equation, which is that y is equal to y0 e to the power of minus kt. And what you need to understand is they're not telling us what I originally started with, but they are telling us that of that original amount, 10% has decayed. In other words, 90% is still left. So you could actually go and you can say, if this was 1, then only 90% would be left, so this would be 0,9. And that's actually the easiest way to do it. You just go and say 90% is left of the original 100%, which is 1. And then I'm going to say it's e to the power of minus k. And now please note, we've got the value of k there. So I know it's pretty awkward to write it in there, but we're going to have to just say it's 1,216,048 times 10 to the power of negative 4. And there's t. Because the question they ask now is they ask very clearly, how old is the sample? So I'm trying to solve for t. And if I'm trying to solve for t, that's now what's left in the equation. That's what I need to solve. Okay, so first things first, obviously 0,9 divided by 1 is just going to give me 0,9. So this is not a problem. If I want to solve that exponential equation, I need to use a logarithm, in this case ln, because the base is e. So I'm going to end up saying minus 1,216,048 times 10 to the power of negative 4. T is then going to be equal to the ln, because I changed that from an exponential to a logarithmic, and the base is e of that 0,9. And then to finish up, all I need to do is divide this by that. Now, if you've cleared the screen from the original answer, then obviously you can use those 6 decimal places, because 6 decimal places is pretty accurate, and you are allowed to use a rounded off version as long as it's scaffolded. As long as you go from B to C, you're allowed to use that. So on my calculator, I will then just type in, it's the ln of 0.9, closing the bracket, divided by, and now to type that part in, I'm going to put a minus and then a bracket as well. And please remember, this scientific notation is given over here on your calculator with that times 10 to the power of x. So I'm going to type in 1.216048, and then you type this button, which already gives you the times 10 to the power, and then I'm going to put the negative 4 there. You could have also just used your normal exponent button there and typed in times 10 and then use the negative 4. It really doesn't matter. I press equal, and it tells me that the time is equal to 866,42. And then learning from my previous lesson, I'm going to quickly just read it again and see, have they given me any instructions on how to round it off? So they just ask how old is the sample. They don't tell me to the nearest year or anything like that. So I'm going to keep the answer correct to 2 decimal places. They did, by the way, if you look at the memo of this paper, they rounded it actually off to 866. They said, let's round it off to 866. I honestly don't think they can penalize you if you rounded it off to 866,42. Because like I said, nowhere in the question did they state they wanted it rounded off to the nearest year. So that was then the 2 questions on this particular paper. Now we have one more paper to look at. This one specifically is my, already did that one. Sorry, slightly disorganized at the moment. There's the other one. So this is specifically over here, it's my IB 2016 paper, and we are going to be looking at these 2 questions. Now, technically speaking, I don't actually have to go and look at this question at all. And the reason I don't have to look at this question is there's something so incredibly similar in your textbook that we've already covered in the textbook examples. I am just quickly going to show you that what we would do over here, if you look at this part, I think you'll recognize that from the textbook example, is we are going to have to go and we are going to have to just change that so to make the base e and make the number x. And that's that part where I write it as the reciprocal. So just quickly to show you over here, I'm not going to solve the whole thing, but just to show you the conversion over here, we're going to go and say it's 2 ln of x, and you'll see just now why I moved that 2 to the front using that law 3. And then this one, careful people, because a lot of people make this mistake. Most people want to go and write the 3 in the fraction, because remember, we're going to write it as a fraction, and we're going to say we swap the e and the x around, so it's the ln of x. So lots of people just want to put the 3 at the bottom. People, the 3 is not part of the logarithm. The 3 is being multiplied by the logarithm. So when you change it to the ln of x, that 3 needs to go up to the top over there, and that's going to be equal to 1. Now, the rest of this is very, very similar to the textbook example. So I actually want you to go and try this on your own. Like I said, all of the memos of these papers are available on the Sicilians Maths website. So you can go and you can try it on your own and you can go and check the answer. But like I said, I don't want to make this video too long, and I'd much rather focus on this question. So in this particular question, it says, determine the domain and range of the graph of y is equal to ln bracket e squared minus x squared. Now, domain and range. The domain of these functions are actually the easy part to answer. And the reason the domain is the easy part to answer is it has to do with the values of x. And you should hopefully know from the definition of a logarithm or a ln that whatever number I put in here has got to be greater than 0. Oh, and can't be equal to 0. So please be careful. It's got to be greater than 0. The moment I put a negative number into a logarithm, and I can show that to you. So if I go the ln of a negative number, it tells me it's a math error. It's undefined. So we can't do that. Or the moment I go and I say, I put into ln, I put the value of 0 specifically, then you'll see again, it's a math error. So that means we need to make sure that that e squared minus x squared is greater than 0. So let's write that down. So specifically focusing on the domain here, we're going to say e squared minus x squared. It's got to be greater than 0. And this, people, don't get a fright. That is actually just a plain straightforward quadratic inequality. So it's a quadratic inequality. By the way, you could go and you can just swap this around, which does make it easier to solve. So I'm going to go and say it's x squared minus e squared. But be careful. I divided by a negative there, divided by a negative there, so that means I need a sign change over here. I'm going to factorize it, saying it's x plus e, x minus e is less than 0. These become my critical values, if you recall. So these are my critical values, and because of my critical values, I'm then going to go and say, and by the way, you don't have to necessarily draw this. I think most of you can get to the answer without drawing the number line, but I'm looking for the negative answers, and you'll recall it's positive, negative, positive. So that means x is going to be located between negative e and e. Now, one little word of warning. And that one little word of warning is when we wrote this and we said that's got to be greater than 0, we also need to just check the following. If I type in the ln of 1, is that an accepted answer? Yes, it is. So there is a restriction that you guys need to be aware of on the base of a logarithm. So if you go and you say log and I make the base 1 and then I make this like 5, that will also go and say math error, because I have a restriction saying that this base over there cannot be equal to 1. Luckily, we know the base over here is e, and e is not equal to 1, it's 2,718, so I know this is safe. So I can just write that out, and then I look at it and I go, okay, x is an element from negative e to e, that's my domain. Now, in order to do the range, you can look at a couple of things. And what you can look at is you can look at this. And we haven't really spoken about this. But ln is a logarithm. And because ln is a logarithm, I can actually draw a nice quick diagram of that logarithm. And I did in the initial notes on e and ln, I showed you guys that e will look like this, which means if I then draw the inverse of that function, it's going to look like that. So very important, we can see this. Now, I completely agree, you've got that e squared minus x squared. So because you've got that e squared minus x squared, you don't necessarily know if this function will look like that. Because whenever I add or subtract something to x, my asymptote, and I'm specifically looking at my asymptote there, it moves left or right. But what you can potentially see over here is you can see that this goes all the way down to negative infinity, this goes all the way up to positive infinity. Now, this unfortunately doesn't necessarily present us with the answers we've been looking for. So what I'm quickly going to do is I'm quickly going to change this into the inverse function. And there's a very good reason for this. So let's do that first. I'm going to say if y is equal to the ln of e squared minus x squared. Then inverse means I change y to x. So that's my inverse. And I change x to y. Now I need to make y the subject of the formula to get that inverse function. So to do that again, remember there's a little e there. So e to the power of x is then equal to e squared minus y squared. So there we go. Now I'm going to go and say it's y squared is then equal to e squared minus e to the power of x. And then lastly, I'm going to go and say y is equal to plus or minus e squared minus e to the power of x. Now why did I do all of this? I'm looking for the range of this function. So the range of this function, if you recall what happens with your inverses, is going to be the domain of the inverse. So listen again. I'm looking for the range of this function. But the moment I've changed this function to the inverse, which is this, I know that the domain of this particular function is going to be the range of that function. So if I look at the domain of this function, I end up with e squared minus e to the power of x. And that has got to be greater than or equal to 0 because it's underneath the square root. So it's got to be greater than or equal to 0. Now, just a quick heads up. Normally we would go and we would say it's greater than or equal to 0, but there might be, because of the original functions, there might be additional restrictions. And those additional restrictions has to do with the fact that if you look at y over here, y in the original one over there, or maybe I should rather go and say, okay, let's stick with this for now, but what you need to understand is we'll check it just now. Once we sub it back, we'll make sure that this works. So now we go and we say, if I find the domain of the inverse, I'm going to be able to find the range of this one. So again, I'm just going to solve this by saying e squared is greater than or equal to e to the power of x. Now, this looks, as you recall, like a normal stock standard exponential. Now, the only problem I've got here is a lot of people will just go and say, oh, I've got e, let's just drop that and change that to x is less than or equal to 2. Let's change it to that. But now you have to be careful. And the reason you have to be careful is we don't actually know what dropping those bases would do to the sign. Maybe the sign changes around. So if this is the first time you've seen this, then you might want to go and just do a quick test to see if this will actually satisfy the inequality. In other words, I want to see if a value less than or equal to 2 will satisfy this. So you can go and you can say, okay, e to the power of 2 is equal to 7,389. So I'm going to write this down, 7,389 ... And I want to know if I take x over here to be a value less than or equal to 2. So I'm going to say, let's make x equal to 1. So I'm going to go and say e to the power of 1, which you don't actually need the calculator. This is going to be 2,718. So I've got that 2,718. So my question is just simply, if x is less than or equal to 2, does that then mean that this is less than that? Yes, it does. So I know this is my answer. Now again, like I explained to you guys, we want to check the range. And we want to check the range saying that y is therefore going to be the same as this x. So I want to reiterate again, the domain of the inverse, which is what I calculated here, is going to be the range of the function, which just means I need to swap the x and the y. So I need to do that. Okay. Now, like I said, there might be additional restrictions to it. So if you look at the top, then you go and you say, can y be less than or equal to 2? If you look at that, yes, it totally can be less than or equal to 2. But there's another little problem. If you start messing with this, is it possible for a logarithm to be negative? Is it possible for a logarithm to be negative? And it is in fact possible for a logarithm to be negative. And the reason it's possible for a logarithm to be negative has to do with the fact that if I go and I put in over here the ln of a fraction value, so let's just do 0.5, then I can have a negative. So it is possible for y to be negative. So I'm going to stick to that answer. I don't have the memo with me, so I'm truly and really hoping that is the correct answer. You might